So welcome all again to week 1 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IUR Bombay, and I'll be PMRFTA for this course. To begin with, as you know, this course covers lot of like wide variety of topics in mathematics, but initial few weeks are dedicated to linear algebra. And here are few books that I personally find very useful for linear algebra. And if you want to go beyond the scope of this course and want to learn more about linear algebra, you can refer to these books. Sorry. Yeah. So the first book is Linear Algebra by David Seeley. This book has many great examples. So the books that I have written are in increasing order of more mathematical. So this last book contains more mathematical understanding of this linear algebra, and the initial book by David Seeley has more of examples rather than this mathematical base. Okay. So for current course, you can go for this book by David Seeley. It has many solved examples and many unsolved problems also. So you can refer to this book. Okay. Second book is by Gilbert Stein. This is a very famous mathematician from MIT. Most of you might have looked at his videos on YouTube. They are like very great videos. Okay. 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 So I'll begin with defining what is called as a vector space. So linear algebra is nothing but the study of vector space. So to begin the study of vector space, we first must know what is vector space, right? So I'll give you a very like lucid kind of explanation. This is not a very formal kind of explanation. So in linear algebra, you need four things. Okay. First is you need a set called V, which is a set of vectors. Okay. Then you need a set called F, which is a field, or you can just imagine it as a set of scalars. Okay. Third is an additive operation. And last one is your multiplicative operation. Is it not visible to everyone? Can you see whatever I'm writing in the presentation? Okay. Pratmesh, you can try rejoining. Then I think it would be visible. Yeah. Okay. So I won't go into a detailed like definition, but I'll give you an idea what a vector space is. You can anyway look for the detailed exact definition in any book. So how does this idea of vector space originate is like like in 12th you might have read about R2 space. Okay. So where you have two elements as vectors. Okay. So we want to generalize this notion of R2. Okay. And see what is meant by a vector space. So we want to study structure similar to R2 or R3. Okay. So three-dimensional vector. So we want to generalize the study of these kind of spaces, for which we come up with the definition of Vinay. Yes, these sessions are recorded, and the links would be updated on the course webpage. Okay. Okay. So we want to generalize the notion of this thing. Okay. So we come up with something called as a vector space. So if you remember, like if you have a vector in R2, for example, 2, 3, then what all you can do with this vector? Okay. You can add it to some other vector. Okay. And you must get a vector within R2 only. Okay. So the first property that any vector space should satisfy is that it should be closed under these operations, additivity and multiplication. Okay. So if you have any two vectors v1 comma v2 from V, then your v1 plus v2 should always belong to V. So this is the first basic property of your vector space. Okay. The second property is that it should be also closed under multiplicative operation. Okay. Now, if you remember your 12th class or something, if I say you to multiply two vectors, then you have multiple notion of multiplication. You have dot product, you have cross products. So we don't want to generalize those things, but we want to generalize something known as scalar multiplication. Okay. Now, if I ask you to multiply, let's say 2 by 2 comma 3, most of you know the answer. Okay. So this is 4 comma 6. So the idea is that if you multiply a vector with some scalar, okay, then you should get a vector within V itself. Okay. So if you, let's say you multiply C into V, then you should get a vector in V itself. So this is the two most basic property, that is closure under additivity and closure under scalar multiplication. Okay. And the rest of the properties are quite intuitive ones. Like if you relate these two, if you imagine that x and y are your vectors in R2 space, something like this, then those vectors are definitely commutative. So what we want is that whatever additive operation we are defining, that additive operation should also be commutative. Next is associative. So most of the time you need not remember these all properties, but yeah, you can anyway refer to this list of 8 to 10 properties and you can check whether a space is vector space or not. The most important ones are that it should be closed under your addition and scalar multiplication. Third property is that you should have a vector that you can call it as a zero vector. So if you add that zero element to any vector, you should get the same element. So what is a zero element? I'm not sure how many of you are from math background, but so if you add a zero element to any element, you obtain the same element. Okay. And this is true for all x. So irrespective of x that you're choosing, if this property is satisfied, then this is called a zero vector. So in a vector space, you must have a zero vector. Okay. Next thing is that you should have an additive inverse. Okay. So what is additive inverse of 2? Like you would have studied it in school. So if you add minus 2 to 2, you get 0. Okay. So same is the definition of additive inverse in a vector space also. So if you have x, let's say, then y is called its additive inverse when if you add y to x, you should get 0. Okay. So this is the definition of additive inverse, that x, so if you add y to x, then you should get 0. So in a vector space, what is required is that you should have an additive inverse for every element in x. Okay. Yeah. Okay. So these four properties are done. Okay. And so like when we combine these four properties, we can call, we can just give it a simple name and call it as an abelian group. I think sir mentioned this name during his lecture, but I thought I would elaborate what an abelian group is. So like if you combine all these 4-5 properties that I have told till now, they fall under an umbrella called abelian group. That is different thing. Yeah. So just to understand this thing more, so an abelian group would have closure property. Okay. It would be commutative, associative, and it would have zero element and an additive inverse. Okay. These are 4-5 properties. Now we will get to the properties related to the symbol of multiplication. Okay. So with respect to this addition, we studied 5 properties. Now we have this multiplication thing and we have some properties associated with it. Okay. Okay. So now if you look at this multiplication, then what we want is we want a multiplicative identity. Okay. Okay. So what is a multiplicative identity? Like in your school days, when you multiplied 1 with any number, let's say you have x and you multiplied it with 1, you will always get x. Okay. We want the same thing for our vector space also. Okay. So if we have a element 1, if we multiply it with any element, we get the same element, then 1 is called as multiplicative identity. Okay. Okay. Now this multiplication should be associative. This is another property that we should satisfy. And the last two properties are, so with respect to multiplication, you had these two properties, that the identity should exist and it should be associative. The last two properties are mixture of addition and multiplication, and these two are your distributive properties. Okay. So these are many rules, right? These are a lot of rules. These are 8 to 10 rules. So what are the takeaways that we can have, so that when we are solving problems or when we are applying it in real life, we can see whether this is a like vector space or not. Okay. So as I mentioned initially, so the true properties that you should look at is closure property. Okay. So closure under addition, and second one is scalar multiplication. Okay. Okay. This is the most basic thing that you should expect out of a vector space. Second is, with respect to addition, this should be commutative, associative. You should have additive identity that you can see as 0. Okay. And you should have additive inverse, right? Now, with respect to your multiplication, that is scalar multiplication, this should be associative and multiplicative identity should exist. We don't require multiplicative inverse in a vector space. Okay. Because we are not multiplying two same things. We are multiplying a scalar with a vector. Okay. And there are other properties, which is distributive property. Okay. So if you have a set V along with a set of scalars which satisfies these properties, then you can call this combined thing as a vector space. Okay. Now, why do we need these kind of tedious definitions or those kind of things? Because if we impose these kind of conditions, then we have further results, which when we apply, it makes our life simpler when we are solving a higher order problems. Okay. So let's say if we want to, I'll just give you an example. Let's say if you are working on some problem where you are working with polynomials. Okay. Now, if I'll tell you something, okay, if I, let's say, give you a task that find the angle between this line and this line, then it won't be very difficult for you to find the angle between these two lines, right? All of you can find. Let's say if you have 1 comma 2 as a vector and minus 1 comma 2 as a vector, if I tell you how to find the angle between these two lines using whatever you have studied till your school level, you can just calculate the dot product and do those cos things and you can find those things. But let's say if you are working somewhere with polynomials, okay, so your data set contains polynomials or those kind of things, and somebody asks you to find angle between two polynomials, then how are you going to find angle between two polynomials? So if we now construct a vector space out of polynomial, then we can extend this notion of dot product to dot product of polynomials. Okay. So whatever properties dot product between these two vectors in R2 is satisfying, if we use the same properties now to calculate the dot product between two polynomials, then we will be able to find the angles between those two polynomials. Okay. So defining these like large number of properties will later help us calculate many things on different kind of structures. Okay. So these things will be clear when we look at the particular examples. Okay. Okay. Like anybody has any doubt related to a definition of vector space or whatever I talked till now? Okay. So here we come up with our okay. What I was saying is, I think when I'll like go for an example, it would be more clear, but I'll just give you an example. So let's say you have a vector, let's say 0, comma 1 and 1, comma 0. Okay. And somebody asks you to find angle between those two. How do you find angle between these two? What you do is you take dot product of these two, and that is equal to cos theta between these two, right? Because this would be also divided by length of this 0, comma 1. And you need not raise hand, you can just type it in the chat box or unmute yourself. Okay. Okay. So this would be 0, right? Cos theta is 0. So angle is your 90-degree. You know this thing, right? Now let's say you have two polynomials. One is f1 of x, another is f2 of x. Then how do you find angle between these two polynomials? Okay. So what we can do is we can construct a vector space out of these polynomials. So we know that R2 is a vector space. Okay. So these vectors are elements of a vector space. Okay. So what we will do is we will construct a vector space of these polynomials. Okay. You will get this thing more clearly when we will solve the example, but I'll just give you an flavor right now. Okay. So if we are able to construct a like vector space out of these polynomials, then next what we can do is using the notion of this dot product, now we can define a dot product between polynomials. I'll give you an example of a dot product. So one of the example is integration of 0 to 1 fx comma dx. So sorry, fx into, so if this is f1x, this is f2x dx. Okay. So this will give you the value of dot product that you obtained using this rule over here on the R2 side. Then you can use the same thing to obtain the angle between these two polynomials, right? So this is what I was saying, that once you are able to mold this thing into set of a vector space, there are many properties that you can straight away use from the setup of R2. Okay. Okay. So I'll go through some of the examples and non-examples of vector space. Okay. So like if the main motivation behind defining this vector space was that we want to make things similar to R2 or R3. So the first example that can come to our mind of a vector space is Rn space. So rather than having two elements, we have now n elements. Okay. So if you take collections of all such vectors, then this forms a vector space. You can check that this will satisfy all these 10 properties that I have mentioned. Okay. So closure is obvious that if we have two vectors of length n, okay, if you will add them, you will get a vector of length n only. Okay. So so the closure is satisfied, right? At least for the addition part, because we are doing pairwise addition. Now for the scalar multiplication also, this thing is satisfied. Okay. So this is an example of our vector space. This is quite an obvious example, right? Now here is another example. As I was talking about this polynomial, now we are talking about function spaces. Okay. So this is the first example of a non-Rn kind of a thing. Okay. So let's say if we have a set S, okay, over some, and we also have some field. So what is a field? I'll skip right now. It's a mathematical entity. So I'll skip right now. You just imagine a field as something like set of real numbers. Okay. Let's say you have a set S, okay, and you have some function that is from S to R. Okay. Now you have some functions from S to R. So as I mentioned, in order to define a vector space, we need four things. First is V, F, plus, and a multiplication symbol. Okay. Now, if we want to transform these functions into set of a vector space, then we will need these four things, right? So we know what our V is. V is any non-empty set, that is S. We have a field as our R. Now we need to define addition of two functions. Okay. So let's say if we have f of x and g of x, we can define f plus g of x as f of x plus g of x. Okay. And we can define scalar multiplication as just you calculate f of x first and then you multiply it by scalar. This is sort of intuitive, right? Now, if you look at these two definitions of addition and multiplication, then is it closed under these two operations? First question that should come to our mind is it closed under these two operations? Okay. So our first operation was uh, addition. So if you calculate f of x plus g of x, this is also a function. It is taking x and giving you a number where this belongs to R, this also belongs to R. So their sum also belongs to R. So f plus g is also a function from S to R. Okay. So the closure property is satisfied. Okay. Similarly, if this f of x belongs to R and these things also belong to R, then multiplication of two real numbers is always a real number, right? So this product will also belong to R. So among our properties that we wanted to check for vector space, closure is done. Okay. Next thing, we come to addition. Addition had four properties. First was commutative, associative, identity, and inverse. Okay, we'll check one by one. So now if you look at the commutative thing, now these two elements, so right, so f plus g of x is nothing but f of x plus g of x. Now this and this are elements of R, real number, and real numbers are commutative, right? So we can write it as g of x plus f of x. Okay. So because we can write it like this, then we can write it as g of f plus x. Okay. So this thing is obviously commutative, right? Similarly, you can also show that it is associative also. Okay. Now, what would be the identity element for this kind of function? Okay. So what we want is we want f plus, let's say we call it as e, okay, of x. We want this to be equal to f of x. Okay. This is what definition of identity is. Okay. Now, if we break the left part, this is f of x plus e of x is equal to f of x. Now, if you take this thing this side, what does this mean? E of x is 0. So, f of x is equal to 0. This particular function is the 0 function for this particular vector space. Okay. Similarly, if you want inverse okay, then you can take f of x is equal to minus f of x. Okay. Similarly, you can prove other properties of vector space also. So if you come to multiplication, I'll complete this example completely so that you know how to prove this thing. So if you look at multiplication, we needed two things. One was associativity. Another one was multiplicative identity. Okay. Now, what would be the multiplicative identity for this kind of setup? What you want is that Pf of x should be equal to f of x. Okay. So if you break the left hand side according to the rule mentioned above, this should be f of x. Okay. What does this mean? She should be 1. Now C is an element of real number. Just remember that thing, that this multiplication is with the scalar. Okay. Okay. Now associative also, if you take C d of f x, isn't this same as C d f of x? This is quite straightforward. If you just break this thing, this left side would be d into f of x into C. This is C d into f of x. This is nothing but the right hand side. Okay. So this is how you can check each and every property and infer whether a particular object that you are given is a vector space or not. Okay. So I won't take a lot of time here because we can do many more interesting problems in our time. Okay. So I'll do this particular problem. Okay. So I began with this polynomial example, right? I'm giving you a like set. Let's say we take V as set of all polynomials of degree 2. Okay. Is this a vector space or not? Okay. We want to check. Okay. So what is the first thing that we had to check? First thing is closure thing. Okay. So let's say you have x square plus 2. This is an element of this set of all polynomial of degree 2. So this is a polynomial of degree 2. So this is an element of this set. Okay. Let's take this as f of x. Let's take this as f. Okay. If we take g as minus of x square plus 2. Okay. Then what is f plus g? F plus g is x square plus 2 minus x square plus 2, which is equal to 4. Now, is the result that we obtained a polynomial of degree 2? The answer is no. Okay. So now if we look at the set that I wrote above, that is the set of all polynomial of degree 2, this is not a vector space. Okay. But initially I told you that we can transform polynomials into vector space and use property of a vector space. So for that we defined a structure that we generally denote by P underscore R. So this is set of all polynomials up to degree n. Okay. So what is up to degree n means? That let's say if you are looking at set of polynomial up to degree 2, so you are also including polynomials which have degree lesser than 2. Okay. So that when you add them up, if the higher order gets cancelled, you still have whatever you obtained is an element of this set. Okay. Now this is quite straightforward, right? Now that if you have any two polynomials up to degree n, then if you add them, you can't go beyond degree n. Okay. So if you have x square, no matter what c you take and you add x square to this, you can't get x cube out of it, right? You can get lesser, but you can't go higher than this. So this set that we form, this is called P and R, and this is a set of all polynomials up to degree n. Okay, so this is a vector space. Yes, you can say that it would be up to degree n minus 1. Then you can use the notion P of n minus 1 R. So that is a different vector space. So, okay, then that would be a different vector space, Vinay. Okay, so yeah, just a second, somebody has joined. Hmm. So let's say you have P3 of R, then how would element of this set look? This would look something like x square or x cube plus x square, or something like this. But if you say up to n minus 1, let's say P2 of R, then it would just contain x square, x plus 1, or something like that. So this is up to degree n. Okay, so you can also include degree n, but you also have polynomials of degree lesser than n in that set. Okay, yeah. So then this particular thing forms a vector space. Okay. Okay. Now we talked about like any doubt in whatever I have covered till now. You can type or unmute. Okay. Now I'm beginning slightly mathematical, but in the later part we will solve most of the questions. Okay. So I'm just kind of building the base right now. So if we look at subspace, what is a subspace? Now we looked at what is called a vector space. Let's say we now have a vector space V of R. Let's say we already have this vector space. Okay. Now if you have a subset of V, okay, that like which is a subset of V, and it satisfies all the properties of a vector space. Okay, under the same operations, addition and multiplication. So this vector space was under some plus and multiplication. Under the same operation, your U also satisfies all property of a vector space. Okay, then we call U as a subspace of our vector space V. Okay, then U is a subspace. Okay, so this is a definition of a subspace, that U must be a subset of our original set, and it should also be an vector space with respect to the same operations that we had with for V. Okay, now why do we like why I have introduced subset is, if you know a bigger set is a let's say vector space, okay, then in order to check a subspace, you need not check all 10 properties. Okay, you just need to check this one particular property and you will be done with it. Okay, so if you know, let's say W is a subset of V, then you just need to check if Cx plus By is an element of W for all C comma B belonging to real number and X comma Y belonging to your vector space W. Okay, so if you just check this particular property, then you are done. Okay, so you all must have came across system of equations, right? So let's say we have 2x plus 3y is equal to 0, or x plus y is equal to 0, something like this. Okay, so if you look at the solution space of this set, okay, this solution space generally forms a vector space. Okay, if you have this coefficients on the right side equal to 0, then this forms a vector space. Okay, now if we want to like sort of check whether this would form a vector space or not, if we go on verifying all the properties of vector space, it would take a lot of time. So we just check this property, that Cx plus By belongs to W. Okay, Let's see how checking this property actually works. Okay. So this is a example from last year's assignment. So we have been given our V, that is the original subspace, sorry, the original space is a vector space. Okay. Now this particular thing we are given that it is a vector space. We are asked whether, so let's not consider this example. We want to check whether these four are vector spaces or not. Okay, we want to check all these four. Okay. So we are given the first one is that W1 is equal to XYZ such that X minus Y minus Z is equal to 0. Okay. Now look carefully. If you look at the structure, this W1 has element of form X comma Y comma Z. So how would an element of X, this W1 look? X comma Y comma Z. So is W1 a subset of V first of all? Yes, because V is R3, so three-dimensional vector. So which has three elements, and W1 also has three elements. Okay, so W1 is a subset of V. First thing is clear. Okay, now what we want to check is whether it is a subspace or not. Okay, so what property we have to check? We have to check Cx plus By belongs to W1 or not for all x comma y in W1 and C comma B in real number. We want to check this particular thing. Okay, so let's check. So how will we check whether this belongs to W1 or not? What we will do is, on the right hand side we have some property related to W1. So if we have any element of W1, then that should satisfy this particular condition that x minus y comma z is equal to 0. Okay, so what we will do is we will check whether any element of this form Cx plus By satisfies this property or not, if my x and y are elements of W1 already. Okay, so first of all let's take x is equal to x1 y1 z1. Okay, and take y is equal to x2 y2 z2. Okay, now what we want to do is we want to write Cx plus By. How would this Cx plus By look? This would be Cx1 plus Bx2, right? Somebody is joining. Yeah. Okay, so C times of x1 plus B times of x2. So this is Cy1 plus By2, Cz1 plus Bz2. Okay, this is my element of this. This is Cx plus By, right? What I want to check is whether this particular property is satisfied or not. Okay, so let's take x minus y minus z, that is Cx1 plus Bx2 minus of, so the second element is getting subtracted, so this is minus Cy1 minus By2. Now the third element is also getting subtracted, so this is Cz1 minus Bz2. If we rearrange this thing, what we can obtain is, this is C times of x1 minus y1 minus z1 plus B times of x2 minus y2 minus z2. Now, as we know that our x and y were already element of W1, so this x and y would satisfy this property of W1, right? So this particular thing becomes 0. This particular thing also becomes 0. So what is the final answer? C into 0 plus B into 0, which is 0. So did Cx plus By satisfy the property of W1? Yes, because Cx plus By satisfied property of W1, so this thing belongs to W1. So this W1 is a vector space. Okay, this is a vector space. So if somebody gives you some arbitrary set and asks you how to check that this is a vector space or not, or a subspace or not, then you will do this kind of a thing. Okay. So I checked for one. I'll go for second one also, and third and fourth you can try on your own later on. Okay. So the second one is W2 is given by x comma y comma z. Okay. Such that y is greater than x. Okay. Now let's look at. So again we will we considering cx plus vy is equal to, no, see, Jaya, we are not considering cx plus vy is equal to 0. What we are trying to do here is we want to check if cx plus vy is an element of w1 or not. Okay. So what was the property of w1? The property of w1 was that x minus y minus z should be equal to 0. So if we have first element, second element, third element as x, y, z, then x minus y minus z should be equal to 0. So we calculated the first element of, so this is actually x for cx plus by. This is y, this is z. Okay. Then we calculated x minus y minus z, and we checked whether that is equal to 0 or not. Because that thing came equal to be 0, then we can infer that cx plus by is an element of w1. And why are we doing this? We are doing this to check whether this set is a subset or not. So in order to check subset, we just need to check this property that cx plus by should be an element of that particular set. Was I clear, Jaya? Okay. So let's look at this particular example. Okay. Now we have x, y, z, and the property that that we need to satisfy is that the y, that is the second component, must be greater than the first component. Okay. Okay. So again, let's take w is equal to x, y, z, maybe x1, y1, z1, w1. Okay. And let us take any w2. Okay, we don't care about w2 right now. If you see, if you want to look at cw1 plus bw2, now I'll take a particular choice of w1 and w2. Okay. So let's say we take c is equal to -1 and b is equal to 0. Sure, Sriram, I'll try to look for w4 also after this one. Okay. So if you take c is equal to -1 and b equal to 0, okay, then what do we obtain? So this sum comes to -1 times w1 plus 0, that is minus w1. Now let's say I have something like 1, 2, 3. Okay. Now clearly this satisfies this property that my second element 2 is greater than equal to 1. If I multiply this thing by -1, what would we obtain? -1, -2, -3. Now does this set satisfy this thing? This is incorrect, right? -2 is smaller than -1. So we had an example of an element of form cx plus w1 plus b times w2, which is not an element of w2. Okay. So if we take c is equal to -1 and b equal to 0, then the the output that we obtain is not an element of w2. That's why the second set that we had is not a vector space or the subspace of R3. Okay. Okay. Now Shriram asked for a W4. I hope the second example was clear. If there is any doubt, you can type. I'll solve W4 in the meanwhile. Okay. So W4 says x comma y comma 0 such that x y belongs to R. Okay. Such that x comma y belongs to R. Okay. So now like this is written slightly in a different way, but what does this mean is that you have some element on the first position, some element on the second position, but the third position is always 0. Okay. So if you look at what property this W4 must satisfy, W4 must satisfy that its last position is always 0. Okay. Last element. Okay. So let's take two elements W1 comma W2. Let's say it belongs to W4, and this is of form X1 Y1 0, right? Because this is an element of W4, and this would be form X2 Y2 0. Now if you do C times W1 plus B times W2, what would be the result? This would be CX1 plus BX2. This would be CY1 plus BY2, and the last position would be 0, right? So what is the so what do you think, Sriram, whether this satisfies the property of W4 or not? Yeah. So yes, this W4 is also a vector space, a subspace. Okay. Okay. One more important example I wanted to include. Okay. For that, I'll say something where you need to just trust me that I'm saying something that is correct. Okay. So, matrix addition, right? If you have two matrix, let's say 1, 2, 3, 4, and 2, 3, 5, 6, how do you add it? You add first element to the first element. Okay. You add second element to the second element. This is how we do matrix addition, right? So this is 3, 5, 8, 10, right? And how do you do scalar multiplication for matrix? Let's say I want to multiply 2 with this matrix 1, 2, 3, 4. What would I obtain? This would be 2, 4, 6, 8, right? So if you now consider, okay, if you now consider mn cross n of R, what does this mean is this is set of all matrices of size n cross n. So n rows and n columns. Okay. So if you have such a set and its elements are from real number. So this was 1 is a real number. Okay. So these kind of matrices, if you take this set and these two operations, this particular addition that we did just now and this scalar multiplication, this will form a vector space. This I want you to trust me, and you can try proving all those 10 properties. You will easily get it. There is no trick in it. Okay. Now, if you just consider set of symmetric matrices, it forms a subspace. Okay. So you have a question on skew symmetric matrix in your assignment. That's why I'm covering this symmetric matrix example. So what is a symmetric matrix? So first of all, what is transpose of a matrix? So in a matrix, if you look at this particular thing, this is called as a row. Okay. And if you look vertically, this is known as a column. So if in a matrix, you make first row as its first column, okay, second row as second column, like you just twist it, you rotate it 90-degree, okay, then that is called as a transpose of a transpose matrix. Okay. So for example, if you have 1, 2, 3, 4, what I told you, we'll make first row as first column, so it's transpose. If you write a T on its top, it is called as transpose. You will get 1, 2, 3, 4. This is something that is known as transpose of a matrix. Okay. So what is a symmetric matrix? So a matrix, a square matrix means you have same number of rows and columns. Okay. A square matrix is called symmetric if A transpose equal to A. Okay. So even if you rotate it, you will get the same matrix. For example, let's say I had 1, 2, 2, 1. So if you just calculate the transpose, still it would be 1, 2, 2, 1. Okay. So these kind of matrices are called symmetric matrices. Okay. So if you look at the set of symmetric matrices, they also forms a subspace. You can try this by just calculating Cx plus By, where your x and y are symmetric matrices. Okay. So you can verify that this position would be same as this position in your x and y. Then in the sum also, these positions will be same. Okay. This is just looking at the matrix addition. It's not tough. Okay. Okay. So symmetric matrices are subspaces of this M and N cross and R that I defined, which is the vector space of all matrices of size n cross n. Okay. So it is subspace of this particular set of matrices. Okay. So, so far what we have understood is what is a vector space and what is a subspace, not much, right? So now after we have like initially, as I told you, that after we transform something into set of a vector space, then we can utilize its properties, right? So now we are going to look at those properties related to those particular vector spaces. Okay. So we can call it as a vector algebra. So I think vector addition, all of you know that if you have two elements, let's say 1, 2, 2, 3, then you can add, this is related to R2, right? Okay. Or Rn for that matter, you can extend it to Rn. Then you can add them element wise. Okay. So this is 3 and 5. So vector addition, I think all of you know. If we go to dot product, okay, I'll give you an example of Rn. Okay. Let's say you have two vectors x1, x2 belonging to Rn. So this has n elements and y again has y1, y2, yn. Then you can define multiplication between these two. So there are other ways of also defining multiplication that you know as cross product. Okay. Or you can come up with other ways also. But one way is called as dot product, denoted by a dot between x and y, and it is given by x1 into y1 plus x2 into y2. So you multiply the first element with the first one and then you add them and so on. Okay. So this is called as a dot product. Okay. So I'll take an example. Let's say my x is 1, minus 1, 2, and my y is 2, 2, let's say minus 1. Okay. Then what is x dot y? So this is first element multiplied with the first element, that is 1 into 2, okay, plus minus 1 into 2 plus 2 into minus 1. So this is 2 minus 2 minus 2, which is equal to minus 2. Okay. Nidish, yes, dot product and cross product are very much different. So in linear algebra, we generally use dot product, you might have came across cross product in your class 12 physics and mathematics. So in linear algebra, we generally don't come up with notion of cross product because uh, yeah, we generally don't come up with the notion of cross product. Okay. Okay. So now one thing that I'm not covering here because this might not be very essential for day-to-day life machine learning, but somebody who is working on a research level or like in your master, you might want to know what is generalization of a dot product. So in R2, you know how to find dot product between these two, but let's say you have vector space containing polynomials or functions. Okay, then how do you find dot product between these two things? That you can like if you want to search, you can search something called as inner product spaces. Inner product. Okay, so inner product is a generalization of dot product that then you can apply to any arbitrary space. Okay, so like we can't cover the complete linear algebra in 1 week, so it would be like if somebody wants to use, you can note it down and read it in the books that I mentioned. Okay. Second thing that we want to know associated with a vector is length of a vector. Okay. So the particular formulation that Sir discussed in his lecture, and I want to repeat, is something known as Euclidean length. Okay. So let's say you have a vector x given as x1, x2, x3. Then what is length of x? Length of x is nothing but x1 square plus x2 square plus x3 square and under root of this complete thing. Okay. So so let's take an example. If we have x as 1, 2, 3, then what is its length? It is under root of 1 square plus 2 square plus 3 square, which is 1 plus 4 plus 9. This is square root of 14. Okay. Now, for length also, you have a generalization that is called as norm of a vector. I'll probably give you one or two examples. So this is called as the Euclidean norm. Okay. This particular thing that we use for R2 is called as the Euclidean length or Euclidean norm. Okay. You can also have something as this is called as one norm. Okay. So of x is given by modulus of x1. So you want the absolute length plus x2 plus x3. Okay. This is called as the one norm. So you can have many definitions of length. Okay. So for example, if you have x is equal to minus 1 comma 1 comma 1, then what is its one norm? One norm is mod of minus 1 plus mod of 1 plus mod of 1, that is 3. Okay. So you can also have something called as p norm. So this is x1 to the power p plus x2 to the power p plus x3 to the power p whole to the power 1 by p. Okay, this is something called as p norm. So if you look at this Euclidean norm, okay, and you replace p by 2, you say x1 square plus x2 square plus x3 square to the power 1 by 2, which is square root, right? So your Euclidean norm is nothing but 2 norm. Okay, you can have like if somebody is interested, then you can look for the term norm and you'll get many materials related to it. Okay. Okay. Now next thing is angle between vectors. Okay. Okay. Now, let's say you have two vectors a comma b, okay, and you want to find angles between these two vectors, okay, then what you can do is, if you have dot product between two this thing, then it is equal to mod of a. This is mod means length of a, okay, so you can use Euclidean length, okay. So if you want to use dot product, the length associated with dot product is always Euclidean length. So if you are using dot product over here, you can't use let's say p norm over here or 1 norm over here. You must stick to Euclidean norm only, okay. Cos theta, okay. So if you send this norm of a into norm of b onto the left side, then we obtain a dot b divided by mod a into mod b is your cos theta. And from here you can obtain the value of theta, okay. So let's take an example where we have a is equal to 1 minus 1 comma 1, let's say, and we have b equal to 2 comma 4 comma 2, okay. Now what is my a dot b? Now my a dot b is 2 minus 4 plus 2, which is 0, right? So what would be my cos theta be? My cos theta would be a dot b, so cos theta is a dot b divided by norm of a into norm of b. Yeah, so this is 0, so for theta equal to 90 degrees, my cos theta is 0, okay. Okay, now the next thing that comes about vector is definition of orthogonal vectors. So we call two vectors a comma b orthogonal if a dot b is 0. So what is the meaning of orthogonal? Orthogonal is that if the angle between these two vectors is 90 degree, then we call two vectors to be orthogonal, okay. So when we have angle between them to be 90 degree, then what would be cos theta? Cos theta would be 0. So this makes this complete term to be 0. That's why we simplify or generalize our definition to obtain that a dot b is equal to 0, okay. Now next is orthonormal vector. So two vectors a and b are orthonormal, okay, if first thing is a and b must be orthogonal, and second is length of a and length of b must be 1. So they must be unit vectors, that is length of these vectors must be 1 and they must be at 90 degree, okay, then they are called orthogonal vectors. So for example, if you look at just wait, if you look at your coordinate system, okay, so you have these two vectors as perpendicular to each other. Let's say these two are your vectors, they are perpendicular to each other, right? Let's call them a and b. So they are orthogonal vectors. You have to ask something, Aditya. Okay, yeah. So now let's say if this point is 1, this is 2, this is 3, and this is 1, 2, 3. Now if I restrict this vector to the length of 1 here and 1 here, okay, then these two vectors are not only orthogonal anymore but also orthonormal, okay. Viveka, you have to ask something.
Sir, at a time, hours after classes will be there. How will manage this course? At a time, this time only,
Okay,
hours
see,
after classes.
see, these are actually not classes. So whatever most of the part that you will learn from the recorded lectures. These are tutorial sessions just to clear your doubts. So what I'll suggest is if you can go through those recorded lectures, and if you have any doubt, you can probably get it cleared. Like in whatever, if, let's say you have registered for two subjects and you have doubt this week in this particular subject, then you can attend this class. So there won't be any attendance or those kind of things for these classes, right? So it's like whatever particular topic you are facing doubt in, you can attend that particular session. Okay. Was I clear? I hope so. Okay. Yeah, the second thing is these sessions will also be recorded on YouTube. And the link, I think this is first is today is the like first lecture. That's why the link is not updated yet. So the link will be updated on the course web page. So you have week 0, week 1, right? Just below that, you will get a link called problem solving session. If you will open that, it will redirect you to the YouTube link. Okay. So those will be uploaded. So this is a 2-hour long session. So probably we can take a break of 5 minutes here. I'll start again at 7:15. Meanwhile, if anybody has any doubt related to whatever we have covered till now, you can please ask. So this course, Essential Mathematics for Machine Learning, is like the professor has done a great initiative trying to cover uh, many like different components of mathematics in just one course. But because we are trying to cover like large like very large portion of syllabus in just 1 or 2 weeks, so there are possibility that you will have many doubts, right? And professor also and me also when taking tutorial can't go in very depth for every topic. So it would be very beneficial for you, like if you come up with your doubt and clear your doubt rather than depending on what I am going to do over here. So then that would be much more beneficial for all of you. So like you can treat me someone who can clear your doubt. So this is not a regular lecture, but I'm here to clear your doubts. Okay. I'll try to come up with good content, but yeah, to gain most of it, it should be more like a doubt clearing session. We'll probably wait 1 or 2 more minutes. See, orthonormal vectors. See, if you look at the application of normalization, when you have, let's say you have a data set. Just give me a second. Let's say you have a data set x comma y, and let's say your x has some 10 features. Okay. Then let's say uh, mm, you have an example of your housing data set, right? So your housing data set, what is the problem in hand is you have some properties of house, okay, and you want to predict its price, okay. So you can have features like number of bedrooms, okay, and second feature can be area area of the house, right? Now if you look at a general house, then the number of bedroom would be something in the range, let's say 2, 3, 1, 2, 3, right? And if you look at the area, it would be in thousands, right? Now, if we want to like learn a, let's say, linear classifier of form, let's call this as x, let's call this as x1, this is x2. If you want to learn a classifier of form a plus b x1 plus b x2 plus c, something of this sort, then the area will influence the parameters a and b. Because the value of area is large, we will try to learn b very accurately, but because the value of a is very small, the influence of this particular term would be small. So what we try to do is, we want to convert everything into range 0 to 1. Okay, so whatever vector that you obtain, right, we try to normalize it. So there you can find use of okay, Vinay. Yeah, so there you can find use of normalized vectors. So one of the popular pre-processing technique is to normalize your data set. Like whenever you train a model, before training, you can normalize your data set. Okay, if you go to something called this orthogonal vectors, while proving many things related to this vector spaces, you kind of get many applications of it. But one application that I can Mayank, this started at 6 o'clock. Okay, so one application I can think of is, so few years back there was a app which you could use to transform your face into a child face or a old age face. I don't remember the app name, if somebody can recall. So has anybody heard of word2vec? Or so what we do is, for let's say if you have an image or some word where the representation is not very great, what we do is we first convert those representation into vectors. Okay, so if the angle between two vectors is small, okay, let's say the angle between two vectors is small, then we say that these two vectors are close to each other. Okay, but if the angle is 90-degree, what we say is that these two words or two vectors are very far away from each other. Okay, so these are the kind of applications where this orthonormal or orthogonal vectors are useful. So that app I was talking about, what that app used to do is, for your face, okay, so they used to find a vector representation, okay, and using that vector representation, they used to move in exactly the opposite direction of your so let's say this is your 2D plane, this is your current age, and old age faces are in this direction. So it will try to project your face in that direction, and then whatever vector that it obtained, it will replicate it back to an image form and will produce you the result. Even this, like if you have a context matching and word matching, there angle plays a very important role. Okay, so in those kind of applications, you find this role of orthogonal vectors and those kind of things. Okay, so wherever angle is involved, orthogonal would simply mean that these two vectors are totally unrelated. Okay, so that is some context where you can use. Another place is when you do this principal component analysis or linear discriminant analysis, LD and PCS. There you want to find representations where the components are not related to each other. Okay, so let's say uh, you have properties of a person, right? So if you have, let's say, height, weight, and let's say you have BMI. Okay, now this vector and this vector won't be related to each other, right? Height and weight are they are related, but the angle won't be very similar to each other, right? But if you look at this combination and the BMI, you can easily figure out about BMI. Okay. So the angle of these two with BMI would generally be less. Okay. So when you can approach this PCA and those kind of thing in this way also, that if you have angle very less between two feature vectors, then you can ignore one of those feature vectors. Okay. So these kind of applications you can think of. Sriram, was I clear? Probably I'll tell you one more thing. So when you do, yeah, okay. I'll give you a very vague but an important statement. So in machine learning, if you look at your, are you familiar with deep learning a little bit or not? So that I know what I'm explaining is correct. Just you can type yes, not. Okay. So in a deep learning, what happens is you uh, give a vector as an input to a let's say neural network. Okay. And it gives you some output. After learning something, it gives you some output. Okay. One thing that you remember is the input that you are giving is a vector. Okay. The input is a vector. Okay. In some cases, it also accepts matrices, but most of the cases, the input is a vector. Okay. Now, let's say if you want to process an image, okay, or a word, okay, or for instance, if you have a video or a sound clip, okay, then these are not vectors, right? Okay. What we try to do is, let's say we have a word book and we have a word notebook. When we hear these two words, what we know is these two words are very related to each other. Okay. What we want to do is we want to convert these words into some vectors. Okay. We want to convert these words into some vectors. Okay. So while converting these words into vectors, we want some properties to be satisfied. What is that property? The property is if two words are related to each other in English, let's say book and notebook are related to each other, then whatever vectors we obtain for book, let's say this is V book and this is V notebook, this should have a very less angle between them. Okay. So angle plays a role over there, that when you map these things into vectors or representations, then the angle plays a very important role. Okay. So there is not a specific application of this orthonormal thing here or orthogonal thing, but because angle also have this orthogonal component, so if two words are orthogonal, that means they are very unrelated to each other. Yeah, because they are related, we want angle to be very small. We map them this way. So, so this representation learning is quite common these days and very famous right now. So this vectors and angles have a lot of applications in this representation learning or those kind of things. Okay. In medical image also, yeah. So when you convert these images to those, if you are using this CNN kind of idea, then they can have different applications. But if you use your multi-layer perceptron or those kind of things, then this vector ideas come into picture. Okay. Okay. Okay, let's proceed further. And yeah. So next topic that we are going to cover today is linear combination of vectors. Okay. So let's say you have a vector 1 comma 2, okay, and you have some vector 2 comma 3. Okay. Now if you multiply this thing with some scalar, okay, and you multiply the other one also with some scalar and you add them, you will obtain something. Okay. Now if you take all such combinations of 1 and 2, these two vectors, let's say this is v1 and v2, then you get linear combination of these vectors. Okay, this is set of all linear combination. So linear combination of two vectors v1 and v2 is nothing but if you multiply first one with some scalar plus you multiply second one with some scalar. This is something called as linear combination. Okay, and if you take all such possible, then this is called set of linear combinations. Okay, so for example, this is 0 1 and 2 3, then if you write 2 times 0 1 plus 3 times 2 comma 3, this is a linear combination of this vector and this vector. Okay, so very related thing to this is linearly independent and linearly dependent vectors. Okay, I'll write 2 3 vectors over here. This is 1 0, this is 0 1, this is 2 comma 3. Okay, let's call this as v1, let's call this as v2, let's call this as v3. Can you write v3 as a linear combination of v1 and v2? Okay, so if you see, if we take 2 times of v1 plus 3 times of v2, then what we obtain? We obtain v3. Krishnan, if we take 2 times of v1 plus 3 times of v2, then what we obtain? This is 2 and the next one is 3, right? So we can write this v3 as a linear combination of v1 and v2. Yes, okay. So if we are able to write this, let's say if we have a set v1 comma v2 comma v3, okay, if we are able to write any one of them as linear combination of other vectors, then that set is called as linearly dependent set. Okay, what does that mean is that you don't actually require this v3. Okay, if you take just v1 and v2 and take a linear combination, you will automatically obtain v3. So this is a sort of intuitive idea that a linearly dependent set will generally have an element which can be written as linear combination of other sets. Okay, now how do we mathematically write it? So let's say what intuitively we understood is that c1 c times v1 plus some b times v2 is equal to v3. Okay, if we take this v3 to the left hand side, so this means c v1 plus b v2 minus v3 is equal to 0. Okay, so what is the mathematical definition of linearly dependent? We call v1 v2 vn to be linearly dependent if there exists c1 c2 cn not all 0, such that c1 v1 plus c2 v2 plus cn vn is equal to 0. Okay, so this is something called as linearly independent. So like if you look at this definition closely, this is just mimicking this thing. Okay, okay, so this is just mimicking this particular thing, that we are over here we were able to write c1 v1 plus c2 v2 plus c3 v3 as equal to 0, where not all c's were 0, then we call this thing as linearly dependent. Okay, so same idea we carry forward over here. So if you are able to find such c1 c2 cn such that not all of them are 0 and we are able to write them in this form, then this is called linearly dependent set. So a set which is not LD linearly dependent is linearly independent. Okay, so a linearly independent set intuitively would mean that even if you remove one element out of that set, then using the rest of them you can't generate that particular set, then you have lost some information. Okay, so this is the idea behind linearly independent and dependent set. Okay, so before this particular thing, let's take a simpler example. I'll come back to this example. Let's take 1, 2, 2, 3, okay, and this is 4 and 7, okay. We want to check whether this is linearly independent or not, okay. So how do we generally check? What is the basic rule? So what we will do is, let's take this as CV1, V2, V3. Then what we will do is, we'll do CV1 plus C1 V1 plus C2 V2 plus C3 V3 equal to 0. We will write this in this equation and we'll try to solve for C1, C2 and C3. If we obtain all the values of C1, C2 and C3 as 0, so if C1 is equal to C2 is equal to C3 is equal to 0, then we will call this set to be linearly independent. If when we obtain the solution set, if even one of them is non-zero, okay, then it is linearly dependent, okay. So let's write it out. So this would be C1 1 2 plus C2 2 3 plus C3 4 7 equal to 0. Now let's write it out. C1 plus 2C2 plus 4C3 is equal to 0. Okay. Now 2C1 plus 3C2, okay, plus 7C3 equal to 0. Okay. Now let's subtract 2 times of this. Let's say this is equation 1, this is equation 2. If we do 2 minus 2 times of 1, what do we obtain? This is C1 plus 2C2 plus 4C3 equal to 0, and next one becomes 0 plus minus of C2 minus of C3 equal to 0. Okay. Now one thing that you can see over here is, even if we try to eliminate now both of them, let's say we want to make this thing also to be 0, this thing also to be 0, we can't make, because we have 2 as coefficient over here and 4 as coefficient over here. So if we subtract half times this thing, we can make this particular thing as 0, but not this particular thing as 0, okay. So what we can do over here is, you can see that we have 2 equations and we have 3 variables to solve, okay. We have only 2 equations and we have 3 unknowns to solve. So what does this mean actually is that we will have a non-zero solution, okay. So this will have infinitely many solutions, or we will have a non-zero solution. How do we obtain it is, so if we take, let's say, let's take C3 to be 1, okay, let's take C3 to be 1. Then using the second equation, what do we obtain? We obtain that minus C3 is equal to C2, or C2 is equal to minus 1, okay. Yeah. Now if we put this thing back in our first equation, what do we obtain? C1 minus 2 plus 4 is equal to 0. So C is minus 2, C1 is minus 2, right? So like you could have taken anything else over here also, and you would have got a non-zero solution for C1, C2 and C3, okay. So minus 2 comma minus 1 comma 1 is a solution for a particular set of equation. So these 3 elements that you got is actually linearly dependent, okay. Now solving these equations was slightly not very charming, or I would say intuitive. One thing that I would, one trick I can tell you, which is actually not a trick but based on theory that we won't be covering. So let's say if you have some vectors v1 v2, v3, v4, and you want to check whether these vectors are linearly independent or not. Okay. One simple thing that you can do is, first step is you write it in a matrix. Okay. So your first column is v1, second column is v2, third column is v3, and fourth column is v4. Okay. After writing it in this form, you take determinant of that matrix. Okay. All of you might know how to calculate determinant. Okay. If somebody don't know, please let me know in the chat. So if your determinant is 0, okay, then your matrix, yes, Varun. Okay. So if your determinant is 0, then the matrix is actually linearly dependent. If it is not equal to 0, then it is linearly independent, whatever set of vectors that you have. Okay. So this has something to do with the rank of this vectors that we obtained, or the how we write these equations. But you can just take away this, that if you write it in form of a matrix and your determinant is 0, then it is linearly dependent. If it is non-zero, then it is linearly independent. Okay. Now, one thing is that you can do this only if your matrix is sort of n cross n, right? Okay. If you have same number of equation as same number of these vectors. Okay. So 1, 2. Okay. So we can try this particular example. So here we have element as 1, 3, minus 4, 2. This is 2, 2, minus 4, 0. This is 1, minus 3, 2, minus 4. This is minus 1, 0, 1, 0, right? Now straight away calculating determinant might not be very easy for this. So what we will do is, we will do some row operations on this. Okay. See, there might be many things also in the the original lectures and this tutorial, which we are skipping. For example, elementary row operations and finding determinant. If somebody is not very comfortable, again I would recommend this first book. This is Linear Algebra by David Seeley. Just go through the first chapter or the first two chapters, and the things would be very clear to you. Okay. Okay, getting back to where we were, or like if you even then if it is not clear, in the discussion forum you can just comment that these things are not clear, and I can take up those things in subsequent lectures or the subsequent tutorials. Okay. Okay. Now what we will do is, we will do some elementary row operation to simplify this calculation. Okay. Now the last one has only two non-zero rows, so we'll try to make them 0. So if we take R3 goes to R3 plus R1 plus R2, so we are adding the first two rows to this thing. Why I am doing this? Because I had minus 4 here, and I can say these two add up to 4, these two add up to 4, and I want to make most of the element as 0. Okay, so then the determinant calculation becomes easier. Okay, so this is 1, 3, 0, fourth row remains as it is, 2, 2, 0, this remains as it is, 1, minus 3, 0 again, this remains as it is, and this one becomes minus 1, 0, 0, 0. Now you can see one of my row has completely become 0. What does this mean? The determinant that I would obtain is 0. Okay. So because the determinant was 0, these four vectors are linearly dependent. Okay. So yeah, if you would have solved it using the equation method, then you would have four equations in four variables, and you would have used more time to solve it. You can just use this thing. Okay. I have 20 minutes left. I'll come back to this dependence and independence towards the end, and let's say what other things we can cover. Okay. Okay. One small thing, very small thing. I think most of you must be aware with matrix multiplication, but for somebody who might not be aware, I'll just tell you how it is done. I'll take a very simple example. Let's say I have 1, 2, 3, 4, 5, 6, 0, 1, 2, and 1, 0, 2, 2, 1, 2, 0, 1, 1. Let's say this is a very, okay. So you will obtain a matrix as a product of two matrices. Okay. How is the first element calculated? Okay. So to calculate your first element, you should take your first row, okay, and take your first column. To obtain this 1 comma 1, you should take your first row and first column. Okay. So whatever position you are obtaining, you will, let's say you want to compute 3 comma 2, that is your third row and second position, then you should take the third row and second column. Okay, third row and second column. Okay, and you take dot product between these two things. Okay, so what you do is you multiply 1 with this 1. So this is 1 into 1 plus 2 into 2 plus 3 into 0. So you obtain 5 over here. Okay. Similarly, if you want to obtain this position, then you will take this same row, okay, with this column now, okay, for this position. So it would be 1 into 0, 0, 2 plus 3, 5 again. Okay. So this is how you multiply two matrices. Okay. Now one thing you should notice is that in order to multiply this particular row with this column, you should have same number of element in this row and in this column. Okay. So number of element in this row is your number of column, and the number of element in your this thing is number of row. So for you to be able to multiply two matrices A and B, number of columns of first matrix A should be equal to the number of rows of the second matrix. Okay. So uh, so how do you write first of all size of a matrix? So let's say if you have a matrix like 1, 2, 3, 2, 6, 2, what is size of this matrix? Size is always written as number of row into number of columns. Okay. So its size is, there are two rows in it. Rows are always horizontal things. Okay. So this is 2 cross 3 columns. So 2 cross 3. Okay. So if your A is 2 comma 3, or let's say if your A is M cross N and B is P cross Q, then for A to be multiplied with V, your N should be equal to P. That is, number of columns should be equal to the number of rows of the second matrix. Okay, just a basic thing. Okay. Now we move to something called dimension of a vector space. Okay. Okay. Now we studied about what is a vector space, right? Now we have something called as basis and dimension of a vector space. Okay, let's say you have a vector space VE. Okay, then you can have a set whose linear combination can generate complete of V. Okay, for example, let's say you have R2. Okay, if you take two vectors, let's say 1 comma 0 and 0 comma 1. Okay, then linear combination of these two vectors, you can generate all of R2. Okay, for example, I'll show you an example. Let's say you have some 5 comma 6, then you can just take 5 times of 1 comma 0 and 6 of 0 comma 1, right? So this linear combination, by this linear combination, you can generate any element in R2, right? So this is something, this is the first property of a basis. Okay, so what we want is, okay, that we want a smallest set so that we can generate all elements in that particular vector space. Okay, so let's say if you had set something as 1 comma 0, 0 comma 1, and let's say you also had 1 comma 1. Okay, now if you look at this particular set, you can still generate all elements of R2 using these three elements, right? But if you can generate all the elements of R2, okay, just using these two elements, then why do we need the third element? Okay, so we are looking for the smallest possible set which can generate all the elements. Okay, so a set S is called basis of a vector space V if S generates, or I would say if V is linear span of S. So that is, if you take all the linear combination of your set S, then you obtain nothing but V. Okay, and the second thing is that your V is linearly independent. Okay, am I clear with definition of this thing, basis? Okay, so if you look at Rn, so we have something called as standard basis. Okay, standard basis. So what is, okay, now another thing is number of element in your basis set is called dimension of that set, the dimension of that vector space. Okay, so your Rn is an n-dimensional vector space, that is, it has n elements in its basis, and you can have more than one basis also for a particular vector space. Okay, so I'll be just mentioning the standard basis. Okay, yeah, S is linearly independent. So standard basis for Rn is that for the first element you take 1 at the first position and 0 everywhere else. Okay, for the second element in the basis, you take 1 at the second position and 0 everywhere else. This way you will obtain n elements, and this is called as the standard basis for an Rn. Okay, similarly, if you have PNR, we talked about PNR, that is polynomial up to degree n, right? So what is a basis for this? So let's say you want to construct x, let's say we are talking about P3R. Okay, so we want to construct something like x cube plus x square plus 1 or x plus 1. So what are the components that you would require? In basis, we must have x cube, we must have x square, we must have x, and we must have 1. So this is called as the standard basis for PNR. Okay, for PNR. This is for P3R. Similarly, you can write for PNR. So what is the dimension for this particular thing? Dimension is n plus 1. Okay. Now last one, we'll come to set of matrices of size n cross m. Okay. So first element you can write as 1 at the first position and 0 everywhere else. Second, you can write 0, 1 and 0 again everywhere else, and so on. So you can construct a basis. This is again called standard basis for MNR. So how many elements would it have? It would have n cross m element, and hence the dimension is n cross m. Okay. 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 One example again more that I'll do is the dimension of your space of symmetric matrices. So in assignment, I think there is a question where you have been asked to find the dimension of a skew symmetric matrices. Okay. Okay. So I'll do for the symmetric matrices, and you can similarly try for skew symmetric matrices. Okay. So one thing, whenever you have been asked to find dimension but not explicitly the basis, okay, so when you don't have to write the basis explicitly but you just need to find the dimension of some subspace, you just remember one thing, that dimension is equal to number of independent choices. Okay, so your dimension is nothing but equal to number of independent choices. This particular line will help you solve, I think, almost every problem where you have to find a dimension of a subspace. Okay, what is meant by the number of independent choice? Okay, let's take this example, then we'll get back to the skew symmetric one. This will help you understand it better. Okay, now we have this first example where W is A, B, C such that A plus B plus C is equal to 0. Okay, now this set has 3 elements that you have to decide upon. Okay, you have A, B and C. There are 3 things that you need to fill in, right? And you have some condition associated with it. Okay, now if you look at this equation A plus B plus C, okay, then you can transform this equation as something as A is equal to minus B minus C. So if you fix your B and C, then your A is already determined. Okay, so how many choices can you make in this particular thing? You can have choice for B and C, but as soon as you fix B and C, your A is already determined. Okay, so how many independent choices you have? You have 2 independent choices in this case. Okay, if you have one equation, because one of your variable get fixed when you put in one equation, so you have 2 independent choices. Okay, now because you have 2 independent choices, the dimension is 2 over here. It is as simple as that. Okay, so your dimension is nothing but the number of independent choices. Okay, now similarly for the second one, if you look, so your W is nothing but A comma B comma C, which is A is equal to B is equal to C. So the condition that is given to you over here is A is equal to B is equal to C. Okay, let's say you fix something A. So let's say you took A is equal to 1. As soon as you take A is equal to 1, your value to B get assigned equal to 1 and value to C get assigned to 1. So how many independent choices you can make? You can make only one independent choice. So as soon as you fix A, all three of them get fixed. Okay. So what is the dimension of this set now? This is 1. Okay. Now we will use the same concept to find the dimension for symmetric matrices. Okay. Let's say we have an n cross n symmetric matrices. Okay. So let's say this is my n cross n. This is my diagonal. Okay. So what is my property of symmetric matrices? That if I take it transpose, it should be the same matrix. Okay. So what does that mean? So whatever element I have over here, I should have over here. So that when I convert my first row to first column, this thing should get mapped. Okay. This diagonal thing is okay. So this second element should get mapped to this thing. Similarly, this element should get mapped to here. Okay. So this thing should get mapped to here, and so on, right? Ahmadi, this is for n cross n. So the sixth value that you are giving might be for some particular n. Okay. So on. So if you look at this thing, so if you look at what are the independent choices that you have to make, okay. So you can make choice for this particular row. Now for the second row, this thing you have already determined. When you fill in the first row, this position you have already determined. Okay. So for the second one, you have independent choices beginning from this point, right? Then you have in the third one, you have beginning from this particular thing. Okay. So how many choices you have for the first one? You have n choices that you can make for the first row. Okay. For the second row, you can make n minus 1. For the third one, you can make n minus 2, and so on till 1. So this is 1 plus 2 plus n. What is the sum of first n natural number? I think it is n plus 1 by 2. I'm not sure about this actually, but it should be n plus 1 by 2. Yeah. So this is how you actually obtain the dimension of some subspace, right? And so the question that is given to you to find this skew symmetric matrices, you can use the same concept, that how many independent choices you have. In that case, in skew symmetric matrices, the diagonal entries become 0. Okay, your diagonals are always 0. So you will have one less choice everywhere. So I won't tell the answer because I'm not allowed to answer, but it would be very easy for you. So you will have one lesser choices everywhere, and you can calculate the dimension for that. Varun, maths, you have any doubt, you can unmute and speak.
Sir, I want to ask that if there is a vector space of matrices, then
Mm-hmm.
we can just divide it into symmetric matrices and skew symmetric matrices.
Yes,
Like
you
two
can.
parts we can do. So the dimension of the whole matrix vector space will be n square. So if we have found the dimension of symmetric matrices, so we can just subtract from n square as well, or we have to find this way only.
It's a good question. So because you can see, the formulation that you have is that for any matrix, you can write it as sum of a symmetric as well as a
Q
skew
symmetric
symmetric,
matrix.
right? But that does not mean the complete space of this matrices is partitioned into two sets, right?
So, but if we will form the matlab vector space of matrices, then either the matrix will be a symmetric matrices or a skew symmetric matrices
No,
in
no,
that
that's
space of n square.
that's what I'm saying. So let's say if you have some matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9. This is neither a symmetric matrix, neither a skew symmetric matrix, right? But this is an element of that particular set.
Yes, sir. So that is correct. But
You can
in a
calculate that way, yeah. I think you can calculate, because let's say this is some symmetric matrices and this is skew symmetric matrices.
skew symmetric matrices, I am forming a vector space
Yeah,
that is contingent of n square.
you can write. You can write.
Okay. Okay.
Okay, so I think we are towards end of our time. So I'll wait for 5 minutes. If anybody has any doubt, I'll be happy to answer that. I'll stop the recording.